Hello.
Hello.
Hi, sorry, I was stuck in another meeting, so sorry if you're waiting here.
I was just about to email to see if.
Hello.
Hey, Maxime. So how are things? Are you Irvine? Is that right?
Yes, I'm in
Yep.
Irvine.
Good.
Are you guys so open for business, or are you sitting
No,
in your?
this is my office/bedroom.
I see.
Do they provide you the
I'll start recording. So it's great to have you here, Chris. He will be talking about how we can learn from Dark Monopoles, and it's from Irvine. So please take it away, Chris.
Okay, thanks very much. So this is, it's good to have finally made it to Minnesota, even virtually. And I'll be talking about kind of a series of papers. I've done some work with John Turning about this. I hope you'll find interesting. Feel free to interrupt me at any time. I've kind of turned off the pictures of you, so I can't see. So just go ahead and speak out and interrupt whenever I say something wrong. So as part of kind of the motivation for this idea, there's probably no need to convince you that there's a lot of evidence for dark matter, that there's something out there that we don't know. And we know a few things about it. We can kind of infer some things from self-interactions and different measurements, but we don't know very much about its particle nature. And while kind of in the early days of thinking about dark matter, there was kind of this notion of it's probably just some simple addition to the standard model. It's just some new particle or particles that make up the dark matter. More and more we think about the concept of a dark sector, that there's some other section of particle physics that it may be very simple. Maybe there's just one or two particles in it, but it may be very rich, just like our sector is, with lots of particles, lots of forces, interactions. The dark sector could be just as interesting and complex as our sector. And so what I'll talk about today is, as a part of such a dark, kind of a rich, complex dark sector, there may be interesting things like magnetic monopoles there, and we might be able to learn some things about them and about kind of magnetic particles in general. Now, there's probably not much I need to motivate this crowd about magnetic monopoles, but just so that we're all kind of on the same page, I'll say a few things about them, about why we might be interested in magnetic monopoles in general. There's, I guess, something of an aesthetic idea that it makes Maxwell's equations more symmetric, if you like, more balanced, if we have both electric and magnetic currents. But beyond that simple aesthetic, it provides, as we learned from Dirac, it gives us an explanation for why electric charges might be quantized. As we look around in the standard model today, every particle that we've ever measured, to within the limits that we can measure them, satisfies this charge quantization. And why might that be is kind of an open question. All of the answers we have are somehow tied back to magnetic monopoles, either that they just exist, or that the charge quantization is tied with grand unified theories, which, if they have to do with our sector, also would predict the existence of these magnetic, typically very heavy magnetic monopole states. And for all those reasons, throughout the years, magnetic monopoles have been sought for experimentally. I have just a few examples of that here from back in the day for some of us, back in 1990, a Tevatron result, and then a more recent Atlas search, continuing to look for these magnetic particles. Of course.
Sorry to interrupt, but I mean, this, I would say the number one, that's Maxwell theory is not the one which by itself you can make symmetric, right? So there is no consistent way to do it symmetrically. So in this way, effectively you can have it like, say, composite monopoles, whatever, but within theory itself, I mean, within U1 theory itself, I do not think that there is a consistent way to describe it.
You mean in the classical or the quantum theory?
No, I mean, if you are thinking about terms of quantum theory, no, I mean, you start with classical theory, and then to try to convert it. So there is no way to make it consistent. This having both magnetic current and electromagnetic current, right? So in a sense, it could be like effective description at a certain distance where You are not trying to go in. So in this, but once you consider composite monopoles, then quantization of charge is built in, right? So this is not a problem then.
Yeah, so that's a good thing to bring up. That's I was going to emphasize this later, that I'm firmly putting myself kind of in the EFT description where things look symmetric. I'm staying away from kind of monopole structure, but yeah, so that's a fair point.
Okay, I'm sorry to interrupt you.
Oh no, that's fine.
It's a minor problem maybe, but still, you see, it was much of discussion, originally, right? So in this way, Dirac monopoles were existing, for a long time, right? But it was no kind of consistent theory how to describe it, right?
Right, and I will touch upon some of those things briefly. I guess I better warn you that I will be talking about Dirac monopoles just as kind of a stand-in for more kind of more sensible things, if you like, kind of as an EFT object. But of course, as we know, we have no, at least concrete evidence or no compelling evidence for the existence of these monopoles in our sector, not yet anyway. But because the dark sector necessarily is there, we have lots of evidence for that, and it could be very rich. There may be magnetic monopoles in that dark sector, and those monopoles might not be completely hidden from us if there is a small kinetic mixing between our visible photon and the dark photon. And that's interesting, I think, for at least two reasons. One is this: if these are somehow stable monopoles, then this gives an interesting and less studied dark matter candidate with some new phenomenology to be interesting to explore and look for. But also as a theoretical laboratory for understanding the interactions between electric and magnetic particles in a perturbative framework, simply because the small kinetic mixing can give us a reason why we have particles that have small magnetic charge to our photon, as well as having small electric charge. And usually in quantum field theory, we don't have that flexibility because of the charge quantization condition. So that's what we're going to explore a little bit. Mostly, I think, actually, part two will be this talk today, but we'll talk a little bit about one as well, point to some phenomenology aspects. So here's what we'll try to do, is I'll talk about some very basic properties of monopoles, and I will be talking about Dirac monopoles for all their issues. That's kind of what I'll use to at least talk about these things. I'll sketch Zwanziger's two potential formalism, a Lagrangian formalism for talking about both electric and magnetic currents at the same time. With that, we'll be able to talk about the kinetic mixing between two sectors where we can talk about both electric and magnetic currents, which will give us kind of the tools we need to talk about these dark magnetic monopoles and how we might actually detect them, how we might search for them. As has already been kind of brought up, this is going to be a talk that is a little bit more pedestrian in some ways. I won't be talking anything about, monopole structure, their composite nature, and all those things. If you like, as has been pointed out, we'll be kind of firmly sitting in an EFT where the monopoles all look point-like to some degree. They look like the Dirac monopoles.
But Chris, it means that in certain way to have some kind of consistency, I believe that it's simple to have in mind that you do have kind of this composite monopoles, but your distances much larger than their sizes. Okay, and that discussing the phenomenology of those distances. This is consistent, right? An example is that say Witten theory, right? You do have monopoles, right? And there is a complete theory, right? But of course you can go to distances much larger than their sizes and discuss their interaction, and it is complete consistency there. However, I'm not sure about consistency of mixing.
Right. That's definitely a good question, and it's something the reason why I'm not discussing this in the disclaimer part of this talk, in a certain sense, is we haven't worked that bit out to make sure that everything works with the mixing from the top down, if you like, from a UV completion. However, from the bottom up, there seems to be a lot of consistency that I think is pretty compelling, and I think we're learning something about quantum field theory, even if I don't have a model I can give you where I can say, we can have the monopoles in both sectors and we see where the kinetic mixing comes from. But from the bottom up EFT perspective, you can definitely put those things in and we're learning something at least about quantum field theory, I would say. But you're absolutely right. I want to, at some point in my life, get to also the UV question, but I've been sufficiently confused with the bottom-up part that we're getting to that part very, very slowly. But certainly there's a lot of work there that someone might be able to do. Okay, so with all those disclaimers and caveats in mind, let me just talk a little bit about what at least a Dirac monopole is. If we're kind of firmly back in the EFT of what things kind of look like. So these will be a little bit basic and I'll go kind of fast, but feel free to stop me. When we talk about, of course, a magnetic monopole, this is just a particle that produces a radially diverging magnetic field in the classical sense. And of course, that means that the divergence of B is going to be 0, because that's what it means to have a diverging field. And classically, that's no problem, but quantum mechanically, this is a problem because we tend to do all of our quantum mechanics in terms of a vector potential that's related to the magnetic field in this way. But of course, that mathematically implies that the divergence of B vanishes. So how do we reconcile these two things? Well, Dirac showed a clever way to get around this. He said, if you really want to have your diverging magnetic field and you're worried about, if you like, the net flux through some surface being non-zero, you can compensate for all the flux coming out through some surface by having a very infinitely thin tube of flux coming in to compensate. And in that way, you can write down a vector potential that gives you everywhere away from the tube, if you like, your magnetic monopole potential or your magnetic monopole field, and kind of have everything you like. So that sounds pretty good. It doesn't quite give us what we want because it gives us a magnetic monopole with a string attached, if you like, which is not what we wanted for. But Dirac might say, well, don't worry about it. It's infinitely thin. It only affects things infinitely close to the string. And if the string is in the way of the physics you're trying to describe, you can go ahead and move it somewhere else. And moving the string from one place to another is just a gauge transformation, so it can't have any effect on the physics. So that's almost true. It's true except it's not really infinitely local. There's one quantum mechanical behavior, which is a little bit non-local, which is that you could see this string through careful scattering experiments. You could see a Aharonov-Bohm phase if you scattered around the string or if you relative to where you scattered not around the string. And so that makes the string look physical, which we're trying to avoid. But Dirac says, aha, there's still a way out of this. If the electric and the magnetic charges satisfy this particular condition, that they're equal to a half integer, then all these Aharonov-Bohm phases will be trivial. They'll be 2 pi I times some integer, and so you'll never see them. And you can really claim that the strings are unphysical. And this is where we get this notion of charge quantization. Now, I should emphasize that you could rightly say, well, this charge quantization just seems to be built around this maybe terrible model of a monopole, and you're right about that. I'm just using it to motivate it. The actual existence of the charge quantization is much more general and robust, but I'm just kind of using this as a way to introduce it for reasons that I think will become clear and that we're going to want to talk about Dirac strings later.
But you know this B of mu, what is for?
Mm-hmm.
You know this B, you are discussing running of charge, or what is for? We
will talk about running a little bit. So thank you for pointing this out.
No, you have formula at your slide, so that's why I'm reacting.
Yes, no, yeah, you're absolutely right. So here we E would be associated with Q, the normally electric charges, and what we'd say is that G would be kind of the magnetic charge that's multiplied by some magnetic coupling that would run in its own sense. But there is a relationship between the magnetic coupling and the electric coupling because of the charge quantization, that they have to be related in this way to preserve this charge quantization condition at all scales. If as Coleman says in one of his papers, if you tell kind of a modern field theorist that there's this charge quantization condition, they'll say, at what scale? Because the couplings run, and so it has to be that.
It's probably true about running, similar running, right? But I would say that it is a scale larger than the size of monopoles still.
Absolutely, that's right. So this is all firmly outside of the monopole. Once you get within the monopole, of course, things must necessarily change. Okay, good. So let's talk about a few other things. As we talk about these magnetic states, and we want to start talking about quantum field theory, we know that it's very powerful to talk or to use discrete symmetries to kind of control interactions or understand what interactions are allowed. And I want to point to some work done by Steven Weinberg back in 1965 when he was deriving Maxwell's equations from just the assumption of a spin-one field. And when he was using the creation and annihilation operators to build up his potentials, he points out that there are two different, if you like, Hermitian potentials that you can construct out of these operators. One is the one that's familiar to us, so-called A mu, which couples to the normal electric currents that we're familiar with. But there's a second potential that you could create, a Hermitian potential that's called B mu. And he pointed out that it was this potential that would couple directly to magnetic currents. But he also showed that this B mu, it transforms differently under discrete symmetries. Specifically under parity and time reversal, it has a relative minus sign compared to the A mu. And this then tells us something about the behavior of magnetic particles under these discrete symmetries as well. If we remember the electric case, the usual electric case, we have some scalar field, and this would be our current. And we know that it has the right transformation laws for the electric current to match A mu if under, say, a CP transformation, phi goes to phi dagger with x going to minus x in the argument. However, if we then take the equivalent type of conserved current, because certainly the magnetic current must be a conserved current, if we took the similar type of form for a conserved current for some magnetic scalar, we need it to transform differently so that K matches B as far as discrete transformations go. And so actually turns out what you need is that phi goes back to itself under CP with x going to minus x instead of going to phi dagger. So this is something different, something we're not always used to, but everything is consistent to make those choices within quantum field theory, and it will have some interesting effects on phenomenology as we move forward. But what does this also mean is that if we're looking at things in the Lagrangian, because A and B have different transformation properties and J and K have different transformation properties, that if you're writing a Lagrangian, you can couple A to J and you can couple B to K, but you can't couple in a simple way A to K or B to J. And so it makes it difficult to write a Lagrangian with just, say, just A mu, because how do you then include the magnetic current? So we'll come to a way around that in just a minute. But before we do, I want to talk about the CPT theorem just a little bit and how we might kind of have a simple mnemonic for thinking about how these particles transform under C and CP.
Yeah, but
it's used.
Yeah.
Go
But
ahead.
at this point, you also should have in mind a duality, because there is a kind of duality transformation which take A to B, right?
That's true. And so what you'll end up having to do then is to also modify your definitions of things like charge conjugation and parity to match those duality transformations. So you're right that these things all exist. You kind of have to do the duality transformation and then define what you mean by parity.
Yeah, no, okay. Again, if you are to say Zabik-Witten theory, you explicitly using this duality, right? I mean, there, it doesn't mean that you have different fields. It is still, no, I mean, degrees of freedom are the same. It is still the same, I mean, the same kind of, I mean, gauge particles on mass shell. However, I mean, okay, it means that this transformation is non-local between A and B, but what I'm trying to emphasize that it is still doesn't mean that you introduce new object. It is still the same photon or whatever in U1 example.
Yeah, for sure. So yeah, you're right. There's if I understand what you're saying, I mean, I'm sure you're right, no matter if I understand what you're saying, but what maybe I can say is that we're going to end up trying to describe the physics, which the physics is what the physics is, and it's all about how we effectively model what the physics is, right? The labels we give things, the fields we use to describe them, the discrete symmetries, that's all us trying to describe the physics. And the physics is whatever the physics is. It's just how we express that, which can be, there's kind of pluses to one language or pluses to another language.
But you see, I think that it is kind of what you are describing here. This slide, it is a sources, and there it could be electric or magnetic. I am not in disagreement with it. What I did try to emphasize that potential, which refers to gauge field, it is just duality transformation. Just making this point that it is not like a different. So you either A or B, because the same theory you can describe as magnetic theory or electric theory, and it is just the transformation of the same theory.
I see. Yeah, this is absolutely true, right? I agree with you. You can have a theory with just electric charges, say, with A and J, and you can do a duality transformation and describe the same theory with just magnetic charges and B and K, and that's absolutely true. The thing that becomes a little subtle or a little bit more confusing, at least to me, is if you have both electric and magnetic currents in the theory. There certainly is still duality, but
I'm trying to give you an example because in Weinberg theory you do have dyons, for example, and dyons has electric and magnetic charge, right? So you certainly, discussing say interaction with dyons, which has both electric and magnetic charge, and it is very much, at least at effective theory, you can do very much consistently.
That's true. And it is also true that kind of the discrete symmetry statement becomes more complicated in that case. I think if you want to have dyons and preserve CP, then you actually have to have pairs of dyons to make the currents work out right. I'm not as much an expert on this, so I'm kind of getting out of my depth about it, but that's my understanding. So I will not be talking about dyons in this talk very much because unfortunately I quickly hit my ignorance about them. But I think one still can use discrete symmetries in a way that's kind of familiar to us who are less familiar with magnetic monopoles, and kind of
right. But you see, in this way, if you have a dion, right, then what you would say for your transformation, which one? Because dion has both. Electric and magnetic charge. Right?
So actually, this is discussed nicely in a paper by Chabachaki, John Turning, and Yuri Sherman. They talk about a dion field of Weyl fermions, and my recollection from their paper is that how you would need to define CP as acting on these fields is that actually you take one dion field into another dion field, and so you have kind of a non-trivial relationship between two dion fields under the CP transformation if you want to preserve CP in this way, which is something you don't need to do if you just have the one. If you don't have dion.
In Weinberg example, dion is a normal composite state, right? Made out of original field. You have your I don't know vector bosons. You have your meta field. So in this sense, if I do once it a particular particle state, right? When I do P, say a discrete transformation. I'm not sure how I can once I cannot go to the other state because implying that this discrete transformation to commute with electric and magnetic charges, I could not go to another dion. You see, because I fixed a magnetic charge, I fixed electric charge, and I'm doing this transformation. So then it should be resolved within, and heat is a composite particle, so you cannot avoid answering this question. Okay, I'm sorry.
No, yeah, I unfortunately I don't think I know enough to address your question, but I think it can be couched in this language, though. I don't know enough to I think satisfy to satisfy you about it. But it's
Yeah.
definitely worth something to think about. But so let's let me just keep going, and we'll see if it seems okay later. I'm going to imagine this, the construction of two different types of charge conjugation operators that I'll call CE and CM, where they only act on either electric particles or magnetic particles. That is to say, they take electric particles to their antiparticles or magnetic particles to their antiparticles in the normal way. And then what we typically think of as the C operator that takes all particles to antiparticles is just the product of these two, CE and CM. So there's nothing too special about that. But what we can also do is we can define parity, the P operator, as being the product of PE and CM. So when I act on an electric particle, this is just the normal parity operator. If I act on a magnetic particle, it operates like parity, but also takes the particle to antiparticle. And a similar thing for time reversal. It's kind of the useful mnemonic as we look at some magnetic states relative to electric states in what follows, is that electric P is like magnetic CP and vice versa. And that's kind of the useful thing to remember. Okay. So as has been kind of pointed out in our discussion so far, there's something of a conservation of pain when it comes to talking about electric and magnetic particles together, about what things you want to make manifest and what things you want to make obscure. So for instance, both Dirac and Schwinger developed kind of action formalisms for dealing with electric and magnetic particles together, but they were non-local in their construction. Zwanziger, sometime later, constructed a local Lagrangian, but at the cost of introducing a second vector potential. So you can have these kind of local couplings between the electric, the electric current in A and the magnetic current in B, but you have to then make sure that you're still describing just one photon using two vector potentials. And in order to do that, you have to end up introducing the space-like vector n to ensure that there's only two physical degrees of freedom on shell. But what we can show is that this n is kind of associated with the Dirac string, which we can make precise, and we will do in a second. But let me introduce you to Zwanziger's Lagrangian. It's a bit more complicated than the usual form of QED, at least looking at the outset. As you can see, there are n's all around doing their job. We have pieces of the Lagrangian that are kind of diagonal in the A or B fields, where each of these f's is just like the normal field strength tensor, which give rise to kind of the normal, or something like the normal diagonal propagators for a photon, coupling between electric charges or between magnetic charges. But there's also another term that mixes A and B, which gives rise to this mixed propagator that connects electric and magnetic currents. And it's this propagator that we'll be most interested in kind of learning about today. Now, I want to emphasize that because A and B have different transformation properties under CP, coupling them together with an epsilon tensor is a CP preserving term in the Lagrangian. And it's only because they have this different transformation laws under P and T that this is the case. The other indices of epsilon being soaked up with vectors, either from the derivatives in F or from N itself. So we can see that everything is making sense as far as conservation laws go, or rather as far as discrete symmetries go. And the point of this Lagrangian is that even though it's complicated and it looks kind of unpleasant in some ways, it does give rise to the correct Maxwell equations that we were hoping for both electric and magnetic currents, though the field strengths for those Maxwell equations are somewhat complicated when written in terms of the A and B fields directly. Okay?
Look, if you consider just say, for example, free electromagnetic field, okay, without sources, okay, sitting in far away from the charges, then there is duality transformation, which tells you that you can write Lagrangian as F mu square in both ways. F mu in terms of potential A would be, F mu dependent on A square, or you can write it as F mu dependent on B square, and it is equivalent theory, right? Because it's nothing but duality transformation, right? and you are not introducing any n in this way, but what is absent, it is how you relate one to another, right? I mean, in this dual description. And when you are doing this, it's written in such a way that in certain sense you can say that A and B are independent field. So let's say that we are quantizing this Lagrangian. How many degrees of freedom you have?
I still just want to have 2 degrees of freedom for the photon, yes.
Right, but then you should have extended gauge transformation to get rid of 2 extra, right? I mean, you have two for vector, right? Normally you have two gauge transformation, and if you take it you have 1 gauge transformation, but it enters twice. I mean, second kind and first kind. So I mean, okay. So essentially 4 minus 2, it gives you 2, right? Okay, if you have, say, 4 now original field, then the number of gauge transformations should be correspondingly I'm not sure how much large, because you can count, right? Because then then you have 8 degrees of freedom originally, and you should have 6. Okay, 6 divided by 2, it should be 3 gauge transformation, right? 3 gauge transformation instead of 1.
Mm-hmm. So what you'll have here is that A and B are have each their separate own kind of, if you like, gauge transformations. You can see that if you look at the Lagrangian, that if you shift A by a gauge transformation,
okay,
it separately preserves B as well.
Yeah, I understand. It gives me 2 gauge transformations, but not 3.
You're right. And so it's the fact that you have this n field that's projecting out another degree of freedom on stuff.
Right, but then I need to see gauge transformation for n. I do not see it.
I'm not sure.
Because you're right that once you are trying to introduce some kind of an additional gauging, right? I agree.
That's right.
Okay.
It certainly is true that n does depend. It does act like a gauge transformation, just like we saw with the Dirac string, right? With the Dirac potential.
It's not realized in explicit gauging, right? Because you are saying that n mu could be transformed, right? When you are doing this in terms of composite particles, you know that it's possible because you start from this Hedgehog configuration, and this Hedgehog configuration could be transformed, gauge transformation, into strings, right? Or into Dirac string. But when you're doing this, you can make, think any direction. You can make think not point like. You can make it like a cone or whatever. There are many ways how we do it. So then is explicitly, but the price you are paying, you are introducing more field, right? Because now you have, non-abelian Yang-Mills field, right? And then indeed you have more gauge transformation. In the form when you kind of reduce it to U1 description, you are losing this.
That's true. And that's a good question. I don't have a good answer for you about how exactly you can see the kind of the transformation.
No, I mean, because I use phenomenology that indeed, because you can put it into things anyway. You're right in terms of approach, right? But I do not know how to realize it mathematically without introducing these extra fields.
Right. Yeah, I don't either.
Okay,
so you've got me there. No, you're fine. You're pointing out all of the flaws, which is exactly what you should do. That's how physics works. And so you're right. There's a sense in which at least I don't understand exactly how it works as far as that goes. But the idea is exactly what you said, that it's the existence of this n field that allows us to deal with the extra degrees of freedom and project them out. But I don't have like a formula that I can write down for you to show it exactly. So unfortunately.
So could I ask a question here then? So given that the Lagrangian looks messy, I mean, at the end of the day, you just want to compute amplitude. So couldn't you just use amplitude techniques to avoid the whole Lagrangian approach?
Potentially. We've looked at that a little bit. I think it's a very good idea. And so what we have done is we've done some basic calculations that should be a good check on that in a certain sense with the Lagrangian formulation. So at some level, you might say, this is a better way of doing it. We have this amplitude approach, and this would be a great check to say there's agreement between the two. Now let's just use amplitudes because it's simpler for everybody.
Exactly, right. And so you're saying that you've already looked at that, you're saying?
We've looked at it a little bit, not deeply. I am not an expert on things amplitude-y. John's looked at it a little bit more. You may have seen this paper he did with some other collaborators about the more general case of kind of constructing S-matrix amplitudes in kind of the full case without the dark side kind of issue.
Yeah.
So I'll say that it's definitely a good idea. The issue that we're going to run up against, as we'll see, is that in the construction that I'm kind of looking at to get this perturbative magnetic charge, you'll find that necessarily the magnetic particles are part of a bound state. They're going to be linked by a physical string of dark magnetic flux, and that seems to me it's probably doable how you do that in the amplitudes language, but I think it's a little bit non-trivial, so it would have to be thought about carefully.
Okay, yeah, thanks.
Mm-hmm.
No, but I mean, to this, we at one point we together with Adam Reitz we wrote some paper about calculating amplitude, for example, interaction of dynes between themselves, right?
Mm-hmm.
Okay, and having in mind something like Zybek-Witten theory, you have a theory and you have composite particles with electric and magnetic charges both. Okay, and then you have a Lagrangian too with this metric tau, and in this way, in some way, you do not need how to say you can describe the result, using this Lagrangian. It doesn't mean you can start from electric description or magnetic description, but what is important there that you have mixing between them as well, because generically when you have both electric and magnetic charges, so you have electrostatic interaction, you have magnetostatic interaction, and you have mixing of interaction. And I'm not sure how it shows in these formulas, but in terms of kind of having in mind this composite dyne, we explicitly calculated this interaction to produce kind of, if you like, amplitude of scattering. No, I'm trying to answer partly Tony's questions that it's possible to do, but I'm not sure about the relation to this particular format. Okay, sorry.
Thanks, Arkady, thanks.
Okay, good. So let me move a bit fast. Let me just say that if you to look at the Dirac potential defined in terms of a string, and look at the background scattering, just use that as a classical background field and the scattering of an electric particle in it, you'll find that the amplitude goes like something like the momentum transfer across n over k dot n, which is exactly the form you see in the mixed propagator of the Zwanziger potential. So this is, I just wanted to use this to tie together the idea that the n from the Dirac potential is really intimately related with the n that shows up in the Zwanziger formalism, even though they seem to appear for different reasons, but there's a tie between them. I'll also mention briefly that this type of mixed propagator was found by Weinberg when he was, again, calculating, just deriving Maxwell's equations. He found the two-point function between these two A and B potentials without any recourse to any Lagrangian whatsoever, and found that it did indeed have this form of an epsilon tensor dotted into to Q and to N, which led him to be puzzled about why this N was showing up in this two-point function, and perhaps as a signal of why there are not magnetic monopoles. Of course, 10 years later, there was explicit construction of magnetic monopoles within quantum field theory. So there's kind of this residual paradox of how to reconcile Weinberg's results with those of 't Hooft and Polyakov. And what John Turning and I did to some degree is to say, well, let's try to test how n actually shows up when you can calculate something to all orders, because the interaction between an electric and a magnetic particle, you're going to have the electric currents or the electric interaction have given you a factor of E, the magnetic a factor of 4 pi over E. So of course, you can't expect the leading term in this perturbation series. You can't necessarily require it to look manifestly Lorentz invariant or gauge invariant. It's only the observables that you can do that. And so maybe you have to actually calculate to all orders to see the Lorentz invariance of these results. And so what we did is we said the only all orders calculation we know how to do is all of the virtual soft photon corrections to a given process. We can calculate that to all orders. If we do, we should be able to see what happens to n and to see if this theory is making sense as far as Lorentz invariance and gauge invariance. And so what we found in doing that, finding all the virtual soft corrections between electric and magnetic particles, is that if you have some given hard interaction, the total interaction is equal to that hard interaction multiplied by an exponential, just as in the case where you have only charges of one type. But the form of the argument of that exponential is significant. You have one term which is n independent, and then you have a second term which does depend on n, but in a very specific way. First of all, it's manifestly imaginary, so that all the independence is only existing in a phase. But second, it turns out it depends on this quantity, which we call L here, which is it's very close to a topological linking number. It's not quite topological, but it's nonetheless always an integer. So it's an n-dependent integer. And what that means, because of the form here, that you have the q and the g for some of these particles, and you have this integer here, that if you have charge quantization, where q times g is some integer over 2, then you find that this phase that you've picked up from n is actually trivial. It's just 2 pi I times some integer. And so at least in the soft limit, we show explicitly that all of the n independence becomes completely trivial when you have charge quantization. So this gives us at least some feeling that it's sensible to be using this Zwanziger Lagrangian, to be talking about these things and talking about physical, well-behaved processes.
Sorry, what is linking with what? You said it's related.
So there's this notion of linking number. If you have two, like in 3 dimensions, if you have just two lines, if you like, you can say topologically whether or not you can remove them from each other. If they're arbitrarily complicated, you can modify them topologically, and either they're linked and you can't fully remove one from the other, or they're not.
Right, I'm okay with that, but what are the 2 lines in question? What are the 2 closed curves in question?
The 2 closed curves in question here are the actual particle trajectories, the electric particle and the magnetic particle, imagining that they are you're kind of associating infinity to be one point, so that they come from infinity, they go to infinity, and infinity is the same place, and that's what's kind of closing the curves in this regard.
I see, thank you.
Mm-hmm. It's a good question. I'm amazed you teased that out after I was going so quickly through this, but yeah, that's a good question. So anyway, that was all just to say that we think that we can use this Lagrangian to say something sensible. And we would like to use it to say something about how we might have this kinetic mixing between our sector and a dark sector. And so what we can do is we can take our ugly, complicated Zwanziger Lagrangian and make things even worse by making 2 copies of it, one for our sector and one for the dark sector, and then consider a kinetic mixing between those 2. But the question is, what does that kinetic mixing look like? If I just have the normal kinetic mixing story, with I have my normal QED Lagrangian, you don't have very many options to deal with. I have F mu nu in the visible sector, I have F mu nu dark in the dark sector, and the only kind of gauge invariant way I can connect them is to have F mu nu dark. But now that I'm using these Zwanziger Lagrangians, I've got my FAs, my FA darks, my FBs, my FB darks. What does kinetic mixing look like?
Is the vector n completely arbitrary in 2 sectors, or is the same vector that you choose?
We're going to choose them to be the same in the two sectors. I think that is just a gauge choice that you can make. I don't know how to think about it sensibly if you don't make that choice, because it would make things much more complicated. So that's a good point. So, but I think that's always a choice you can make. Let us choose to have the ends be the same in the 2 sectors.
to say that there is some kind of extra here, because look, if we are talking about U1 theory, I mean, for the field outside of the source, it's just one field, okay? And in this way, you can mix it the same way as you mix with a normal photon. And what was reflection of stuff was that you can have duality transformation, right? That the same field, which was a field, and then you would write mixing, you know, in standard way, right? F mu A, you know, F mu AD. I mean, as a normal way. Okay, and it would be okay. Then duality allows you to substitute F mu A by F mu B. Okay, and so I don't know. So in this sense, I think that it's the kind of you know, if you know how to say, think in terms of composite monopoles. Okay, think in terms of kind of non-abelian theory, where you have this non-abelian model. You do not need this type of Lagrangian. It will be a different one, and then you can derive, you know, A and B as kind of, you know, as a result of this original field. Okay. And in terms of this non-abelian theory, you can try to introduce mixing anyway, right? I mean, if you believe that you have, say, a kind of non-abelian field, I mean, describing, you know, this, say, kind of Zybig-Witten situation, and then adding up other field and see whether you can consistently do theory of this, like, two non-abelian field or whatever. I'm not sure how to do it, but you see what kind of direction I'm trying to go.
I think I do, and I think we'll come around to the same result in the same way, just in this different language. So feel free to stop me if it seems wrong, but I think your intuition is right, and I think that we'll get to the same result if I understood your comment. And the way we're gonna get to that is we're gonna rewrite the Zwanziger Lagrangian in this way. We're just gonna rescale A and B in this way, so that we've removed all of the factors of the coupling from the current terms, and see what the Lagrangian looks like. And we see that with the FA term has a 1 over E squared, which we'd kind of expect. That's what our familiar, one of the familiar ways of normalizing F mu nu in QED. But FB goes like E squared.
No, but look, if I will try to do what you are saying, for example, using terminology of this non-abelian field, it would be much more harder for me to write this mixing, right? Because I'm not sure how I will write mixing between two non-abelian fields. So I think that it is a way which allows you to see what kind of problem it is in this mixing. No, I'm not sure. Okay, I'm sorry that I'm keeping you from producing your presentation. Okay, the only excuse is that I should leave very soon, and you will be free from me.
we will certainly miss you. But I think again, well, I cannot answer your question directly, because I also don't know how I don't have a model in my mind for how the kinetic mixing would show up from the top down with an actual non-abelian construction, as you say. But at least from the bottom up, I can see what is maybe possible in a certain sense. And so the idea here is that we can see, of course, that as E runs, if you like, the coefficients of FB and FA, if I was going to look at their wave function renormalization, it would run oppositely. And in fact, particularly inversely to each other. And in as much as we often think of the one loop calculation for kinetic mixing being, say, the connection between A and A dark through particles that are charged under both, that this is very similar to the calculations for wave function renormalization in a normal theory. What you can see is that if you were to say that the wave function here went something like 1 over 1 plus pi, or 1 over 1 minus pi, whatever you want to have to define it, for the normal renormalization story, then this would go like 1 minus pi. And so if I expand that to leading order in pi, for like a simple one loop result, perturbative result, then I would have these two terms would show up multiplied by pi, but with an opposite sign. So if you like, the form of the kinetic mixing would be of F dark times FA minus FB dark times FB. And though it's not exactly obvious from the definitions of F mu nu that I gave before, this turns out to be exactly F mu nu times F mu nu dark. And so we can see this form that we could have guessed as being what it kind of had to be based on our intuition from the normal kinetic mixing story is also realized in the Zwanziger Lagrangian in this kind of, again, more complicated way, but still a self-consistent way. You can unmix things. I'm going to go a little bit fast. There is one remaining charge quantization condition. But there's also a freedom in kinetic mixing always. There's this freedom, which here I've given as this field, or this, not this field phi, but rather this angle phi, that there's this freedom on how I want to reparameterize two U1 theories. If I have two U1 theories, I can always make linear combinations of what I'm going to call the photon. And that's just reparameterization. There's no physics involved. And so the physics has to be independent of that. With that freedom to choose phi, I can show that there is a choice of phi wherein there's no physical coupling between the visible photon and the dark magnetic current. And so it must be that when both photons are massless, there is no physical coupling. You could write things in a more complicated way in which it appears to, but as you actually calculated amplitudes, everything would cancel out. So in order to have a physical coupling between the visible photon and the dark magnetic currents, we have to give a mass to the dark photon. That way I can't choose phi independently. There's only one choice of phi, which keeps the visible photon massless. And in that basis, we can then look at what the physical couplings to fields are. So this is what I've written down here. We have the normal story as far as electric currents go, that the visible photon couples just to the visible electric current, and that the dark photon couples to both the dark electric current and has a small epsilon size coupling to the visible electric current. So that is that the visible electric matter gets a small coupling to the dark photon. That's the normal familiar story with kind of these dark photon models, massive dark photon models. But at the same time, the dark magnetic couplings are kind of unaffected. The dark magnetic gauge potential just couples to the dark magnetic charges. But the visible dark magnetic current, or the visible magnetic current is, again, the visible magnetic, yes, the diagonal visible magnetic current includes the visible fields, but also a small epsilon sized coupling to the dark current. So the dark magnetic charge, or dark magnetic matter, gets a small coupling to the visible photon in this way. Now notice that the signs are opposite, which is kind of a vestige of the charge quantization condition. And so this is the interesting result. When you have a massive dark photon, you get a small physical coupling between the dark magnetic current and the visible photon. And it's that small coupling that we want to exploit or use to try to probe dark magnetic currents. Of course, when you give a mass to the dark photon and there are magnetic charges around, it also means that those charges have to confine. That's what it means to give the dark photon a mass, that you'll have a coupling, or rather an interaction between charges of opposite charge magnetic monopoles that there can be connected by a string of dark magnetic flux. A physical string, so this is not like the Dirac string, it's physical, it affects these things, it binds them together with a tension that goes like the mass of the dark photon squared. And so that's going to be important to what follows as well. But just one point about the physical nature of these strings is that they are really physical. I mean, that sounds kind of tautological, but unlike the Dirac string, which because of charge quantization we could never see, or we could always claim is just a convenient mathematical fiction, these strings are real, and so you can see them through Aharonov-Bohm effect. So if you imagine that there are some stable population of these dark magnetic bound states from a dark sector, you can imagine looking for them with precise Aharonov-Bohm experiments.
Can I ask a simpler question? Suppose that the size of the bound state is smaller than the wavelength of the our electromagnetic probe.
Mm-hmm.
Do you have a complete understanding in terms of the multiple expansion, what this system will look like from the point of view? I mean, like, is there a coupling to a photon of like the charge, like charge radius, or I don't know, higher multiples?
Right. It is interesting. So we have a little bit of information about that. I don't know how much time I'm going to have, but what shall I say? If it turns out, so this is kind of in the next section, so I'll just answer your question. It turns out that if you're looking at a spherically symmetric ground state, then if you like, there's no expectation value for what kind of the physical n would be. There's as much n pointing in one direction as another. Everything cancels out. It averages out to 0. In those cases, there's basically no coupling, right, between the electric probe, the visible electric probe, and the dark magnetic bound state. You need to have something which gives an expectation value to a separation.
This can happen for us. So you would then argue that the single photon form factor of such state is identically 0, right? Elastic form factor. However, then the next question, the double photon exchange, right? So if you have such a system, you absolutely will still have some sort of what's called polarizability, right?
Mm-hmm.
Because then you can virtually excite that state and de-excite, right? So
yeah, our belief is that exactly as you're saying, there would be a double photon interaction, there would be a polarizability, and that would give you an interaction. We have not yet calculated it, but we would like to, or someone should, to figure out what that would be. Our kind of poor man's way of getting around it was to say, if you imagine putting an external magnetic field in your experiment, let's say you're doing dark matter direct detection or something like that, put an external magnetic field in your experiment, then that would stretch out your dark magnetic monopoles because they have this coupling to the magnetic field, to the photon, and that would give an expectation value for what n is. And so in that case, you would also have a non-zero scattering amplitude. Okay. So I think both of those would work. I don't know which would be the simplest to do. So how much? I seem to be about out of time. Should I wrap up?
No, I think it's okay. If there's anyone that needs to leave and wants to ask a question, then we can just take this opportunity to do so. Otherwise, I would say we just continue.
Okay. I'll go quick, just highlighting some things so that I'm not taking up everyone's time. But we kind of, this is along very much with Maxime's question. How do we start doing some real interesting kind of phenomenology? How do we extract some physics? How would we detect these things? And all of that comes down to mostly this propagator, right? Because we have electric charges in our sector, and we're interested in finding these magnetic charges in the dark sector. And so we have to deal with this beast here, this mixed propagator. And most of it looks fine. I mean, sure, epsilon tensors can be painful, but that's, we know how to deal with it. The strange thing we have to worry about is that in the denominator we have this n dot k, right? We understand this pole, we believe this pole is physical, but it shouldn't be the case that the orientation of the string could maybe lead to a singularity in these scattering amplitudes. That doesn't make much sense. And so what we wanted to show is that in all physical processes that we could think of, that actually these spurious poles, as we call them, would cancel. And you could make unambiguous finite predictions. that this goes part of understanding how this works is that, or rather, let me say, we'll see that this cancellation of this pole is intimately related to the fact that you're dealing with a bound state. And this goes against our kind of more naive expectation that if we probe the bound state with high energy photons, that we can kind of not worry about the other state, because we're looking at energy levels that are not sensitive to the whole size of the bound state. I can just focus on the interaction between the the electric particle, the electron, let's say, and just one of the monopoles. But why you can't do that is the fact that there is both there's two photons involved, right? So if you want to look at higher energies, then you had better use both the massless photon and the massive photon. So you're going to have, let's say in some scattering experiment, two diagrams, one with the massless photon, the visible photon, that goes like Q and minus epsilon G, and one that goes like epsilon Q for the massive dark photon and G for the photon, or for the monopole. Notice that these enter with opposite sign because of the charges and how these things couple. So what before was just going like 1 over k to the 4 in your amplitude is going to go like 1 over k squared minus 1 over k squared minus mv squared from the massive propagator. And this means that for energies much larger than the mass of the dark photon, that all of these processes are highly suppressed, which kind of makes sense. If you remember, I said that if you had two massless photons, there's no physical coupling between the two. And of course, if I go to very high energies, it's almost as if I don't have to worry about the mass of the dark photon. And so effectively, there's no physical coupling, or rather that physical coupling is highly suppressed at those scales. So I really can't take a decoupling limit in that regard. I have to always care about the fact that this is a bound state and that both the magnetic charges are important. But when I do that, it turns out that these extra poles cancel. And the simplest way to see that is just to, again, imagine a background magnetic dipole field and look at electric scattering in that background field. When you do that in the same way we did before to get some insight into the Dirac string, we see that we get the same form of the interaction, but we get a 1 minus this exponential factor here. The 1's going to cancel off the 1 in the exponential, and every other term as I expand this out in its power series will have at least 1 power of n dot k, which will cancel the spurious pole. And so we'll have a nice finite prediction for any value of n and k. And that's essentially what happens no matter what you do, as I was going to show, but maybe I'll kind of skip past it. But just to make the argument that the poles always cancel when you look at things carefully for kind of similar reasons. We've already talked about this a little bit. So let me skip to direct production, which is the last thing I'll talk about. That again, in direct production, we're going to need to care about both the photon, or the visible photon, and dark photon parts of the production mode. And that's going to give us the same type of suppression of the coupling at high energies. So we have to really think about bound state production. And when we're thinking about bound states, we get a lot of mileage out of looking at discrete symmetries, or using discrete symmetries to characterize the bound states. You may remember, or let me remind you of how, for instance, parity and charge conjugation are determined for different bound states of the electric fermions or electric scalars. And we can use our mnemonic that we talked about earlier to discuss why, or what the parity would be for the magnetic cases as well. Of course, charge conjugation is the same, so all the C's will be the same. But the parity for the magnetic case is really like CP for the electric case. As you multiply these together, you just get this result. Similarly for the scalar case. And we can use this to learn a lot already about single photon production, simply by looking at the possible combinations that exist. So if I imagine, for instance, taking two electric scalars and annihilating them to a single photon that would then produce two magnetic scalars, I can see that on the electric side, I've only got one state that is spin 1, the 1 minus minus state. On the magnetic side, I also only have one state, the spin 1, and that's a 1 plus minus state. These have opposite CP. So there is actually nothing you can write down. CP says you cannot have single photon production of magnetic scalars by electric scalars in this way. It's just completely forbidden. There's no cancellation of the spurious pull in this case. It's just not an amplitude you're allowed to write down. However, in the fermion case, you have a little bit more flexibility. Here you have, in the electric case, both 1 minus minus and 1 plus minus states that exist. And similarly, in the magnetic case, 1 plus minus and 1 minus minus states. So you could imagine that you can have a CP preserving process that goes through a spin 1 state, and that everything would be fine. However, it turns out that that's not the case. But the reason is a little bit subtle. While a magnetic bound state can be in a 1 plus minus, or sorry, electric configuration can be 1 plus minus, it has no overlap with a single photon. So the single photon current can only give you the 1 minus minus in the electric case. The single photon current can only give you the 1 plus minus in the magnetic case. So while you can write down an amplitude that connects these two, you can go from electric to magnetic through a single photon. What you find out as you try to project onto these correct states, that it actually is a vanishing amplitude as well. However, you can show that that actually this vanishing amplitude goes like n dot k over n dot k. So it's unambiguously zero in that case. The pull has canceled and it still vanishes. So I guess the take-home lesson here, sorry this has been so quick, is that single photon production of magnetic monopoles by electric particles is zero. It's a vanishing amplitude in all cases. And so that's something that's interesting to inform kind of the phenomenological investigation. However, it's not that you can never produce these particles. And this kind of also goes back to Maxime's comment about scattering. If you look at photon fusion, if you had 2 photons coming in, there is a non-zero production amplitude for producing 2 magnetic monopoles. And so you can imagine this being one possible mode to produce magnetic monopoles from the electric particles. But you're going to need 2 interactions, which of course will necessarily mean 2 instances of the kinetic mixing, which will affect things. You can calculate, it's not very useful to look at, so I won't show it to you. You can calculate that the spurious poles cancel in this case, as long as you choose n to be proportional to the relative momenta between your 2 magnetic monopoles, which again makes us understand that we're really taking n to be physically this physical string of flux, because if you're in the center of the momentum frame, then the physical string is going to be stretched in between the particle and the antiparticle. And when you choose n along that direction, that's when all of the spurious poles cancel and you get unambiguous physical results. So let me just leave it there and not worry about the summary and ask if there are any other questions.
Yeah, so people should feel, thank you, Chris, for the talk. People should feel free to just unmute and ask questions.
So are you saying that in terms of the phenomenology, so these dark monopoles, they can make up all of the dark matter then? Is that?
They can't make up all the dark matter. Well, maybe they could. The ones we were looking at as a dark matter candidate, we were really hoping to be able to find them just through a Harnaff bone. And in those cases, to maximize our Harnaff bone signal, we needed the strings to be long. The longer the string, the more time you have to see there's a difference. And so in that case, that made their kind of self-interaction cross-sections too large. They just had a kind of a geometric cross-section that was too large. So it could only be maybe 10% of the dark matter to make sure you weren't in conflict with self-interaction bounds. If you let them become smaller, so if the dark photon mass was larger and the binding was tighter, I presume at some point that would go away. And so you could have them be more of the dark matter. I haven't thought that all the way through, but I don't see a problem with these being all the dark matter.
So you were just, so basically the main experimental signal is just to see this magnetic dark sector, right? That's really, and you don't necessarily have to have it be all of the dark matter. You can still just have different signals.
Yeah, exactly. Part of the richness of the dark sector.
Yeah, I see.
Could include these guys.
Yeah.
Are there other questions? If not, Oh,
Yeah,
go ahead.
Yeah, Matthias. Matthias, go ahead.
Oh, yeah, I was just wondering, like, what would be kind of like the minimal model for this? Would be something like a SU2 in the dark sector, and then I guess you break that, and you end up with kinetic mixing between the U1 and the dark sector.
Yeah, that's a good question. As far as the minimal model where you're actually breaking, the SU2 and have kinetic mixing, I don't have a good answer for you. It is on my list of things to do. However, just figuring out that single photon production was 0 took like a year of my life, because we kept on being confused about things. So it's a great question. I don't have a good answer for you, unfortunately.
Mm-hmm. Cool.
I have a few very naive questions. Maybe I spaced out for some of your discussion. But what's the relation between these two fields, FA and FB? Are they, maybe it's related to what Matthias' question. Usually I thought FA and FB are, one of them is the auxiliary field that I introduced to write down ENM with monopoles. However, here you are thinking about there's a physical FB in the dark sector. That is, there's. However, the U1 and U1 prime are in some sense strongly connected to each other because of the existence of a dark monopole.
So I'll say some things and tell me if I'm answering your question.
Yeah.
So the way to think about it, the way I'm thinking about it is, let's say just in the visible sector, forget the dark sector for a minute. You have both FA and FB. And you shouldn't think of either of them as being the photon and another one the auxiliary field. They are both the photon. They're just written in a different, so you're expressing the photon in different ways. You're writing the creation and annihilation operators in different ways, and they are kind of non-trivially overlapping ways. So you have to be able to disentangle, make sure you're not overcounting things, and that's what this whole structure with this complicated Lagrangian is doing for you. But they are both conspiring to just be the photon. So when you're looking at some process, you have to include all the effects from both A and B. But typically, if it's just looking like electric to electric, there won't be a lot of B involved, typically, because it has no coupling to electric particles and things like that. So you really need both fields in both sectors. And so the kinetic mixing is a mixing that involves both the A and the B fields. Is that helpful? I don't know.
Yeah, maybe I think it makes sense to me, but let me ask the dumb question one more time.
Sure.
Am I only gauging one U1, or actually I'm gauging two U1s?
You are gauging one U1, so it's still one U1 gauge theory, though both A and B have a gauge symmetry in a certain sense. You can do gauge transformations on one of them, but they're really, it's just, so we already know that just using gauge theory, you're using some formalism that, I'm using a vector even though I only have 2 degrees of freedom. I'm overcounting, and then I'm being careful to make sure I don't overcount. I'm making it even worse now. I'm using 2 potentials to talk about 2 degrees of freedom. So there's a lot more overcounting, but I'm doing that because there are particular interactions that are clearer in this language. But it is still only one gauge theory. So you're looking at one U1 gauge theory where I'm using 2 fields to describe the vector boson of that theory, the 2 degrees of freedom.
Okay. But I guess what makes this description, like in some sense phenomenologically viable, which defines a preferred basis that I choose to call it, photon, is that I give the other degree of freedom some small mass, and through which mechanism I granted the FV a mass.
Okay, so I'm sorry, I must have I went.
No, but you still have a dark photon. I mean, you have A and B in our sector, but then you have A and B in the dark sector. So there still is a dark photon, Zhen. I think is that what you're asking? I mean.
Yeah. I'm confused about how many gauge symmetries I have.
Well, there's still 2, but each the dark sector has 2 polarizations. Our sector has 2 polarizations. but then you have these monopole couplings in addition.
Yeah, so sorry, I didn't understand. So yes, this
Yeah,
is a U1
sorry.
cross
Yeah, I was
U1.
just trying to
you were right.
clarify. Yeah.
And I'm glad you did, because I was clearly not helping here. So you're right. This is a U1 cross U1 when I'm involved in the dark sector as well. But each U1 is being described by an A and a B field. So it's not that A is visible and B is dark. It's that I have an A and B in the visible sector and an A dark and a B dark in the dark sector. And I'm giving it electric mass to the dark sector. So I'm giving a mass term, if you like it goes like MD goes like A dark. So I'll give that in the usual Higgs mechanism type of way. There's some field that has a charge.
That makes sense. And we have electric charged fermions in our sector, and we have a monopole in the dark sector.
Mhm.
Is that the critical?
Yes.
Okay.
Yeah.
So yeah, but is that in some sense the monopole in the dark sector is not some dual to of the electron in our sector, or both have the electron and the monopole? It's really dark sector has a monopole, our sector has electron, but they are kinetic mixed. So I have some complex description.
That's exactly right. So if you have it here, like this is the barred currents would be like the currents in the diagonal basis when I've undone the kinetic mixing, and it's written in terms of the mixed currents. So just take in the visible sector K to be 0. There's no monopoles in our sector, and if you like, you can set J dark to be 0. So there's no electric fields in the visible or in the dark sector. That's fine too. And you just have that in the visible sector. What would we see? We'd have our normal electric particles, and then we'd have a small coupling to these dark magnetic particles.
I see. And usually the charge quantization is done in a way that the electric charge times magnetic charge gives me some integer. But here, do I lose the charge quantization condition or still secretly there? But I saw you use that charge quantization condition slightly.
So this is one of the slides I skipped. I apologize for that. But so if you imagine the two sectors are separate, then you could say there's going to be a charge quantization in each sector.
Right.
But actually, when I kinetically mix sectors, I can't require that anymore. I can't necessarily require that that's true. If you imagine doing the same type of experiment where I'm looking for the Dirac string, if you like, then because there's this ambiguity about parameterization when I have two massless fields, in general, both G and Q are going to be talking to both gauge fields, both A and B. So both of them are going to show up in the calculation via Harnaff-Bohm phase. And so what I'll find is actually that the sum, if you like, in the diagonal sector of the barred charges needs to be an integer over 2. But if I look at one part individually, it does not satisfy Dirac charge quantization. So once I mix the two sectors, I'm saying I only have one charge quantization condition. And when I give a mass to the dark photon, I'm going to be breaking that by amounts that scale like the mass. And so if I go below the mass of the dark photon, for instance, I can see that there's a physical string, that there's a physical Harnaff-Bohm phase here. But if I go to very high energies where the mass is not significant, then it looks like I just have massless photons, and it looks like I have a charge quantization condition that would cancel these effects.
Okay, thanks for explaining.
Oh, no problem. I'm sorry that I didn't give this the time it deserved as we were going through.
Yeah.
So can I just ask if you could elaborate further on the amplitude question I asked you? So if there's a quick answer or not. So if we were to do all this with amplitudes, do you know how you would incorporate magnetic charges then?
So I'm not an expert on this, but so it kind of goes back to there's this issue with charge quantization. So there's a great calculation done by, I think, Thomson back in like 1900. He just discovered the electric charge, and so it's like, let's talk about magnetic charges, guys. They must be out there, right? It's a totally natural thing to do. And he figured out that if you just have a fixed electric charge and a fixed magnetic charge, no motion, just fix them, and you calculate the angular momentum in the electric electromagnetic field, that it's non-zero. And in fact, it goes like Q times G. And so this is one way of seeing charge quantization in a very, no potentials way. You just say, if I believe that angular momentum is quantized in quantum mechanics, you immediately get this charge quantization condition just from this simple calculation. And so, but it's this fact that there's angular momentum stuck in the fields when you have electric and magnetic charges that you have to be careful when you're doing the amplitude story. You have to kind of modify the little group discussion to include this angular momentum in the field. So there was this paper recently, like I said, by Chaba and John and Yuri and Michael Waterbury and Zhongwu Hong, where they did this for like the general case, very carefully constructing these little group things.
I see.
But it seems kind of complicated.
Oh,
I don't know how to make that work in a simple way in this case too. There may be a way to do that, but again, I feel like there's this conservation of pain that
yeah, because that's where I was. Yeah, because that's where I was leading to, because I was just wondering if you could then take the amplitude calculation and check your result for the single photon, right? Because you get a very simple result, right? After a lot of pain, you find that it vanishes. So I'm wondering, with the amplitude approach, typically that's supposed to be an order of magnitude easier, right, in computing amplitude. So maybe that result would follow much more simply for the calculation you did. But again, as you say, if you have to add in, I mean, I don't see how you would add in the magnetic charge, but you're saying you got to modify the little group, and then maybe that's already increasing the amount of work you have to do. I don't know. So you're saying that that's probably conserved the amount of pain.
Yeah, it's something that we did look at. We certainly did. We looked, there's this paper by Nima and collaborators where they do like, how to do all the amplitudes for everything. And we tried to look at that and understand it, take the normal electric case, single photon, and look at for the magnetic case. And we just, it was unclear, because it seemed there what you could extract from their method, as far as I understood it, which I'm sure is not how everyone needs to understand it, is that you really were just extracting kind of the residue of the pole of the scattering. And what we really were trying to show is that this extra pole was canceled. And so we wouldn't actually get any information about that, because we were only looking for the other pole, not the first one. And so we made some attempts. We got confused about photon polarizations, about what the actual CP structure of the photon was, because I just found that A and B have different CP structures. What was the physical photon CP structure? I still don't remember what we decided about that. So it's a great idea, but we didn't get it to work. It's not that no one can, but we didn't see a simple way through it.
I see. Yeah, thanks.
Yeah, just to follow up on that, actually, I want to ask you about your comments on those Chaba et al.'s paper, but I think you commented on them already. I think what they imposed on top of what Nima et al. Or just general amplitude people. General amplitudes are written down in this little group fashion, assuming the asymptotic states of single particle. What they find out, the Chaba et al. Find for consistent description of the scattering involving monopoles, you cannot assume I have like asymptotic states of a single particle, like single electron, single monopole. I have to pair them up. Then there's additional constraints on the so-called pairwise symmetry or pairwise. I think to me it's a really angular momentum. So there's additional selection rules and construction you have to put down to call an initial and final state. Then that restricts further what's the final amplitude you can write down. That seem to simplify the way you can write down monopole scatterings. However, of course, that requires a lot of preparation, let's call them, right? To properly define my strongly correlated initial states, right? That are pairwise with long-distance interactions, etc. Then write down amplitude. I don't know. I forgot. I forgot what's my conclusion about whether their results are super usable or not. But that's my impression on what they have achieved.
Yeah, that sounds correct to me. I will say that John was finishing that paper at the same time we were struggling through this one, and we already knew that the single photon production was 0. So presumably, if it had been simple in their language as well, they would have just mentioned it. But I don't know. So,
Yeah. I think it's secretly really just angular momentum conservation.
yeah.
And you just have to project your initial and final states, together instead of together instead of individual particles. That impose more restriction. But I don't remember their discussion about other poles actually. But still, I think your discussion is more intuitive to us more traditional physicists.
Yeah, I kind of feel like it's a bridge in that way. Like clearly that if we want to do this well, we probably need some other language. And this is a way that's kind of closely related to my old pedestrian way of thinking about scattering and calculating through Feynman diagrams, and you can get some results even though it's a little bit painful, and presumably you can do the same thing with the amplitudes discussion, and maybe it's the right language to do everything, but this will be kind of a way of bridging the two and seeing how to understand those results, I hope.
Yeah. I have to say my eventual impression on that piece of work is it's a good alternative description, but it doesn't show more potential in giving us the correct description of monopole physics. That's my impression. I don't know how did I arrive there.
Right.
Okay, I'm going to have to go, but thanks very much again, Chris, for interesting talk. Thanks.
Yeah, my pleasure. Thanks for coming.
Yeah, thanks,
Chris.
All
Can you send your slides to